Good morning, everybody. I'm kind of happy to be the first presenter today. This is my first econ, so I'm not entirely sure what will be going on here, but I tried, from what I gathered, to give you a nice talk. The core of my talk will address a discussion that is coming up over and over again, and the discussion in one sentence is the center pressure and the zero moment point the same thing. But as I consider myself a bioroboticist and am working on biorobotics, I'd like to start with a brief introduction into biorobotics and some peculiarity about bipedal robots. Then, in the main part, I want to talk about points of force application in robotic and human walking, and then explain a little bit the research challenges I would like to address or I'm currently addressing in my research. Okay, so biorobotics, as a German engineer, we always have a standard for that, and there is a standard of the German Engineering Association number 6222 on biorobotics, and it states that robots that possess an implementation of at least one dominant biological principle, and is usually developed based on the biomimetic development process. Okay, so now you would of course like to know what biomimetics is, and also there's a standard, it's 6220, and it also says what biomimetics is, which combines biology and technology with the goal of solving technical problems through the abstraction, transfer, and application of knowledge gained in interdisciplinary cooperation from biological models. So there are a couple of terms that might need further scrutiny. So interdisciplinary is kind of obvious, but it's also kind of the challenge, because if you work in this field, it often seems that you don't belong anywhere. There are now a couple of journals that address the field of biomimetics, but still, if it comes to writing proposals, for example, there often isn't a proper field that addresses this interdisciplinary research. One important part is biological models. So models is something that we have kind of an intuitive understanding of, but models can mean a lot of different things. So they can mean like a model to scale that shows the structure of something. It can be mathematical models, obviously. And the important part, I think, of a model, a friend, a senior researcher, said to me, a model is only a model if it can predict some behavior. So you need to have your model be able to predict something. Okay, so this is like a general overview of what biorobotics is, and also here at the chair, right from the standard of the German Engineering Association, we find an example. This is the fin ray gripper of the Crops robot, and this is named in the standard, and along some description of what that is, the main function is described here. When lateral force is applied to one of the struts, the tip does not bend in the direction of the force, but bulges out instead in the opposite direction. And this is a very nice example of a bottom-up biomimetic development. The guy who came up with this, a carpenter from Berlin actually, was on a fishing trip in Norway when he observed this behavior in a fish. And then he looked into how does that come to be. He came up with a structure. Also a quite peculiar thing about bottom-up biomimetic processes. They had the structure and they didn't know what to do with it. So it took a while until they came up with some commercialization. So Festo is now selling grippers like this. Also, Veleda, the mopping company, is selling like a bucket that rings your mop with the help of these devices. And there are manta ray robots that generate a very natural flapping motion using these fin rays. So, but what about bipedal robots? And here the norm gets tricky. Because what it says, humanoid and anthropomorphic robots are not handled in this standard, since there is no consensus on the definitions relating to this area of biomimetic robotics. And this, I think, also says a little bit about this field. So we have, I think, like kind of bipedal robots are kind of the tip of biorobotics, as they look like humans. So they essentially try to mimic a human in a very straightforward and direct way. But there are very big differences in how you can understand biomimetic. There are two distinct ways of using biomimetics. One is morphological biomimetics. That means it looks like the natural blueprint. Another is functional biomimetics. That means it supposedly functions like the biological blueprint. And because we have such a big range of different bipedal robots, it is very hard to tell which is which and where it's going. So, just to wrap up biorobotics of course does not only refer to mechanisms, but also to ways of controlling robots, to optimization processes, materials, and so on. So it's a very big field. But obviously, as I said, or I think we can agree that anthropomorphic robots somehow belong in the realm of biorobotics. And when you talk to these roboticists, there's often a controversy. So, as I said, the general question is, okay, one important concept I will introduce in just a moment in bipedal robotics is the zero moment point. One concept that is similar, kind of related from biomechanics, from the study of human gait, is the center of pressure. And comparing these points of force application, as I termed them, and trying to answer the questions that we had during a couple of discussions here, are ZMP and CUP the same thing, is what I'm trying to do in the next quarter of an hour. Okay, so let's first, as not all of you, for a reason I'm not entirely sure about, are working on bipedal robots. Let's just start slowly and get into the challenge of bipedal walking. So the problem you have in bipedal walking is that you have a pretty small contact area, you have a large mass on top of it, you have a pole, which is your leg, and you somehow have to balance your mass on top of this small area of support. And if you want to walk, you also have to move this mass forward, so you have to cope with some dynamics. The interaction between the walker, so in this example me, and its environment is partly unilateral and passive. And what that means is, if I put my foot on the ground, I can only push on the ground, I cannot pull on it, and I have to rely heavily on friction, so in order not to slip away. So this is something, and there is no way. So when I grip something, I can essentially also pull on it, I can turn it around, and I can apply any forces to the handle. In walking, this is not the case. The forces I can apply are really limited. And then, lastly, motion is always some kind, is a result of some kind of friction asymmetry. So we have to modulate our motion by modulating this force we put to the ground. So if you think about it, a rolling wheel has larger friction on the bottom than on the top, and so we get a forward motion. In walking, what we do, we have high friction on the ground, and then we swing our leg forward through the air. This progresses us forward. If you think about snakes, for example, as they undulate, also they push against, in one direction, against the ground, and then move forward. The less friction, you can also translate that to swimming, flying, and so on. It also always comes down to some kind of friction asymmetry or force asymmetry that you generate. Okay. Before getting into the technical details, I would like to talk a little bit about terminology, which is familiar for people that work in this field but might not be familiar for everybody else. So one important thing are ground reaction forces. These are the forces applied onto the ground or from the ground to our mechanism, and the vertical component, as I said, is unilateral. So the nice thing about the ground, normally if the friction is right and the ground is not too soft, the ground will always provide the right forces for whatever I do. So this is really hard to model. This is what I think everybody working with contacts is aware of that, but this is one key set of forces that we see in bipedal walking. This is the force that the ground applies onto our system. The polygon of support. The polygon of support is a convex plane that is parallel to the ground, or is the ground itself, and comprising of all contact points. So if I'm in contact with the ground only with one foot, then my foot will be essentially the polygon of support. I can extend my polygon of support putting a second foot onto the ground, and then my polygon of support will extend from one foot to the other, comprising the entire foot and the connecting lines and the area in between. And last but not least is the timing of walking. Single and double support are walking guide phases with 1 foot or 2 feet in contact with the ground, respectively. Okay, now let's go to the problem statement that roboticists came up with like decades ago about what we should do in order to keep a bipedal walker upright. So we have this planar contact with the ground. It constitutes a passive degree of freedom, and what we want to do is before we want to do anything, we have to acknowledge that this passive degree of freedom is enabling a bipedal machine to rotate about its foot and ultimately fall. So the problem is, if my forces are set to into the wrong place and wrong magnitude, I will be falling over. My foot will be rotating and will be tipping. So the goal for bipedal walkers thus is to prevent tipping by avoiding foot rotation, at least during single support. And the theoretical framework for that is quite old already. So Biorobotics, scientists from Yugoslavia back then, from Belgrade, was essentially providing the theoretical framework for doing that. He introduced, though not naming it this right, in 1968, the zero moment point. In later papers I found that they added tipping to the zero moment point, and this might be more intuitive because I will talk a little bit what the zero moment point is, but essentially what it does, it is a point that tries to prevent the foot from tipping over. We will see how that works. And he published a paper in 2004, essentially reviewing his work. It was entitled Zero Moment Point, 35 Years of Its Life, where he reviewed a lot of the notions of zero moment points and how it was conceived, or how it was conceived and how it was perceived by the robotics community. And most of the quotes I'm using in the following slides are from this paper. So what he says is that the zero moment point aims at preserving the dynamic balance of the bipedal robot by ensuring the foot's whole area, so the sole of the foot is in contact with the ground. And this is essentially what there is to ZMP. So the ZMP, zero moment point, refers to a point with respect to which the angular momentum of the system we observe, so it will mostly be the foot, but for a thought experiment, we will look at something different, is preserved given the current ground reaction forces. So essentially what we try to do is we try to keep some mechanical system that is not tipping, has no angular momentum in the same state by finding a point where the angular momentum doesn't change. Okay, it preserves the angular momentum by definition of a dynamical system at this instance only. So having no change in angular momentum doesn't mean that we don't have an angular momentum. So we can still be tipping, we just look for the point where the angular momentum wouldn't change. And if our angular momentum was 0 before, then we won't be tipping. Okay, and one thing he says in the paper, and this is one thing that we discussed already a little bit, if the real support polygon is not large enough. So essentially my support polygon is limited to the area of my foot. I can't have it any larger unless I put another foot down, which is not always viable. The resulting ground reaction force to balance the action of external moments, so these external moments can come from accelerations of my body in any direction, for example, will act at the foot edge, which can result in the mechanism overturn. Okay, so essentially what we say here is once the mechanism overturns, our 0 moment point is not within the polygon of support, and I will illustrate that in just a moment. Okay, and then also from this paper he says, to clarify the meaning of the ZMP outside the polygon of support, let us be reminded that there are 2 different cases in which the ZMP plays a key role. And this is this is quite important. So the first one is a case that's mostly used in bipedal robotics. So it is used for determining the proper dynamics of the mechanism above the foot to ensure a desired ZMP position. So essentially what we do in bipedal robotics is we say, okay, we don't want our robot to tip over. We put our foot onto the ground, and now we calculate our upper body dynamics in order to keep the ZMP inside the polygon of support, maybe with some safety margin, in order to make sure that we stay upright and balanced. But there's also a second meaning, and this is something I would like to look into today. It is determining the ZMP position of different mechanisms of motion. And this, I think, can tell us a little bit of what is going on and how to work with the ZMP and what the ZMP can actually do. So points of discussions we had over the last couple of weeks was, can the ZMP leave the polygon of support? Are humans keeping the ZMP inside the polygon of support when walking? And are ZMP and center of pressure the same points? So let's just illustrate a little bit what we are doing here. And as a thought experiment, in order to illustrate a little better of what is going on, I just changed the model a little bit. So I'm using a linear inverted pendulum model. It can move here, it can turn around the foot point. It can obviously only apply forces to the ground at the foot point. So we have these ground reaction forces here. We have accelerations here, so we just assume for a moment that we just have an active, some kind of active forward acceleration and gravity acting on that concentrated mass, which is positioned at the coordinates x and y. Please bear with me, I'm using the coordinate system of the International Society of Biomechanics, which is essentially x in the main direction of motion and y pointing upward. I think the reason for that is that for a lot of times we look into sagittal plane dynamics. What is the sagittal plane? The sagittal plane is a term from anatomy again. So sagitta is the Latin word for an arrow, and the sagittal axis is the axis that would extend an arrow that would be shot through you. So I don't know where this comes from, but this is essentially how this goes. And so if you think about this arrow shot through you and you take the vertical, then you get a sagittal plane. And as I work a lot in the sagittal plane, I find it quite convenient to talk about x and y and have z as the rotational axis, but I hope we can work with that for now. So now, how do we define the ZMP? So we have all the influences of external forces in our accelerations here. Obviously, we are tipping, so we are changing our angular momentum, and now we're looking for a point where the angular momentum for our concentrated mass doesn't change. So we look for a point P for which the change in angular momentum of the considered system in motion disappears. So the sum of torques around this point should be 0. We can now formulate the torques of these accelerations and set them to 0, and we get a formulation for this point that we are looking for. If we for a moment reduce the horizontal acceleration to 0, then this point will appear directly below our center of mass, and we would call the center of mass projected to the ground the projected center of mass, and we could think about like the vertical ground reaction forces applying at this point, at this moment, would not change the angular momentum of this mass point, though we still would tip if we have some angular momentum at all. If we add vertical or horizontal acceleration, our point would move forward. You can see that right here from the equation. So we would have to apply our ground reaction forces here in order to not change the angular momentum of our system.
A question, do you neglect acceleration in vertical direction?
No, I don't.
No, you need M and Y double dot.
Yeah, for the moment I say my double dot is exactly my acceleration due to that. But I think like you can add this. This is just for the sake of simplicity at the moment. Okay, so there's one other relevant point that I was mentioning a couple of times, so let's also look at that. So the center of pressure. The center of pressure by definition is located in the planar contact area between foot and ground, so it can't leave this area. And when torques tip the foot, they can be assumed to act around the center of pressure. So we can have torques acting around the center of pressure. And if you look at that, so if we have our reduced model again, the only point where my forces can actually act is this one point down here. And obviously, our moment or the center of mass is experiencing some tipping torque, and on a rigid body that could imagine this torque acting around this foot point. So in order to illustrate this whole concept and in order to see a little bit what is going on, I'm using a little animation, and I would like to talk you through that before I play it. So in order to have a little bit more exciting dynamics going on, I use a standard reduced model from biomechanics, which is the spring mass model. It also has one point at the top of its, or the entire mass concentrated in one point. It has two massless springs, which essentially just generate the dynamics of the system. It's completely passive. There is no actuation. We give it an initial impulse and it will go. The only variable we have to separate, given a set of parameters like leg length, mass, spring stiffness, and so on, is the angle of attack. So the spring is massless, so swinging the leg forward and backward doesn't add anything to the system, but we have to set the foot right at the right angle in order to generate a periodic gain. And what you will see here in the animation is you have the center of mass up here, you have the center of pressure or the ground reaction forces down here. You will see the center of pressure as this green diamond. Down here it will move in double support. You will see the zero moment point and the projected center of mass. And what I also put into this animation is the acceleration of the center of mass, direction of the acceleration of the center of mass, so we can see how it behaves. See? Yeah. Okay, and now we see in double support the center of pressure is moving from one leg to the other. Now the acceleration is moving forward, so the zero moment point is moving in front of the model. We have the projected center of mass, and we have only this one point where all these points coincide, because we have only vertical acceleration here. So essentially, if we apply our forces here, the angular momentum of our system doesn't change. Okay, let's play that back one more time. Double support and single support again. Okay, so this was the introduction into this concept. So the takeaway is, as soon as the angular momentum of the system around all points in contact with the ground changes, COP and ZMP divide. And the ZMP, all torques around horizontal axis cancel each other out. This is the, it doesn't say anything about or much about vertical torques. This is why I think zero tipping moment point might be more intuitive. It also doesn't technically need to be located in the ground plane, but this is the point we are interested in. And then in the given example, the polygon of support is just one point. And in single support and a line in double support. So, and this is of course not what we see in humans or biological robots. So now let's enlarge the polygon of support and see what happens. Yes?
Just one question. When you talk about torques and forces, you include the inertial forces, right?
Yes.
Okay. You call that forces.
Yes. Okay. So what we do now is we extend, we have now a joint which is corresponding to the ankle joint down here at the foot. We still have our body who can do whatever he wants essentially on top of it. And whatever the body does on top of it, we will see as a reaction force in the ankles. Our foot now has a mass which also contributes to the dynamics, and we again have the ground reaction forces somewhere in our contact plane. So the general idea, and I think this is a pretty smart approach, is to say we can neglect the entire mechanism above the ankle, and we can represent it by just the interaction forces at the ankle if we are only interested in the foot not flipping around. So the foot also experiences the ground reaction forces at some point P, whose action desirably keeps the whole mechanism in equilibrium. So this is also taken again from Biorobotics' paper. So as long as we have this image, our mechanism above our foot is generating these interaction forces. We now have an actuated degree of freedom also at the ankle, so we can apply torques and generate a reaction torque. We have our ground reaction forces and the mass of our foot contributing, and now we can essentially just write down, okay, we want the torques around one point, which is the zero moment point, to be zero. So this is essentially the statement for the zero moment point. It doesn't say where it's located yet, if inside or outside the foot, but so just to quickly go through that, so the vector from to the ZMP, where the ground reaction forces needs to apply, and we look only at it for torques around the horizontal axis. So this is why I put a couple of zeros there, neglected the z component at some point. So we have the vector to the center of mass of the foot, and the gravitational force, we have the ankle torque, and we have the joint forces and a vector to the ankle as contributing torques around our foot. And now the observation, which is a little bit counterintuitive at first, but if you think about it, makes sense. So by accelerating my upper body center of mass forward, I can shift my ZMP backward. And so if you think about it, if you hold a large ball with a high mass, you're tipping forward and you're pushing it away from you, it will bring you back up. And I think this might be a way to think about that. Essentially, shifting yourself forward can keep your foot from tipping, shift your center of mass backward. Okay, so now let's remember, the zero moment point is the point where would the resulting force be applied at this point. The ground reaction forces, the angular momentum of our foot would not change. If the angular momentum of the foot is zero to begin with, and it's possible to apply the forces at the ZMP, the foot will remain in its static equilibrium, so you'll have no changes in angular momentum. So now we can find that this is what we do in controls, a set of whole body dynamics which satisfy this constraint by modulating the joint forces and torques. Accordingly, whenever this foot starts to tip, then the ZMP leaves the polygon of support, because then our forces cannot be applied at a point anymore where the change in angular momentum of the foot is not zero. So what Biorobotics says about that, in such situations the acting point of the ground reaction force would be on the foot edge, but this point would not be the ZMP anymore. He calls it a virtual ZMP outside the polygon of support. And now, this is something I'm not sure if that has been done before, I haven't seen it, so what I try to do now is to take experimental data from human walking and compare these different points for a cycle of human walking. There are a couple of caveats. So the first thing is, in experimental data, I have only certain landmarks that tell me where my foot actually is. So I have markers attached to the foot, one at the heel, one at the ankle, and one at the metatarsal joint, which is a toe joint just in front here. And I have to somehow estimate how the rest of the foot looks from that. So this is, for example, while here at the beginning of stance, we are penetrating the ground as the heel pad deforms there. This is something I just do not consider in the animation. Also, the toe region, I somehow have to estimate what is going on there. Besides the markers, what we also measured was the global dynamics, the ground reaction forces. So from the ground reaction forces, we can also determine the center of pressure, which is again indicated with this green polygon. And we know the center of mass of the foot from tables from the US Air Force. They did a large study in the 60s about pilots, and essentially published them telling for each segment of the human body where all the important landmarks and points and dynamic properties, what they are. So this is about the center of mass of the foot and the acting force. The foot is pretty lightweight, so the force is not too big. And now, having the kinematics of my entire body and the ground reaction forces, inverse dynamics can be applied, and I can also calculate the joint forces of the ankle and joint force, obviously. And so, from that, I'm indicating here the overall center of mass position, the projected center of mass of my upper body. So I'm not depicting the entire upper body, legs, trunk, head, arms, and so on, but just the foot, as I do the sign as is done in robotics. I just use a representation of the upper body dynamics from the joint force. I'm also indicating the ground reaction forces as vectors and the joint forces and torques as vectors. They are scaled because they are pretty big, but they are scaled to the same scale. And I will also indicate the torque around the ankle. So you will see this cross moving into an arc here depending on how big the torque is around the ankle. And then we will have the calculated ZMP also depicted throughout the gait cycle. And what we should see is double support. Now we are in single support. We see center of pressure and ZMP quite close to each other. I would say that's probably in a margin of error. Now my foot starts to tipping and going into flight. We will see the whole cycle again in a moment, and then we will focus on single support. So you see the forces acting at the joints and at the ground. You see now the foot tipping, the zero moment point moving a little backwards, and then moving away. And now double support is a little bit tricky because I have the same feet on the same treadmill. I can separate the forces a little bit, but single support is much more indicative. So I would say here, zero moment point and center of pressure are pretty close together. There is a little bit of wiggling in the foot, and now when we arrive at the axis of rotation, and this is really hard to determine where it is, but you see the heel coming up. You see that the zero moment point starts to substantially deviate from the center of pressure, and we get essentially this quite large tipping in single support already in human walking. And this is one step of one experiment, so there is, this is not averaged or anything, just to show what is going on, but this is, I think, to a certain extent representative of what we are seeing in human walking. And one of the main problems I think we have in human walking is that we don't have that defined eye contact surface. We have the experimental setup also adds a little bit of uncertainty, where I would say for the most part ZMP and COP here are designed, but we get this substantial tipping motion. So this is the end of single support. Now in the next frame, the contralateral foot will touch the ground, and already here essentially our zero moment point left what would be left of the polygon of support. And so my conclusion here is that humans do not entirely aim at balancing throughout single support, so they do not avoid to rotate the foot during stance. And just as a takeaway from this main section, so plan for the ZMP to stay within the polygon of support does not capture all features that we see in bipedal locomotion in animals, and I think this is not too surprising. It has, however, been proven to work well for bipedal walkers, and here essentially we have this first point that Biorobotics made. We can use it for gait synthesis in bipedal walkers, and it has proven to be very reliable and can essentially generate very robust and efficient gaits. If we look into gait analysis, we can also see how the ZMP and the COP relate to each other. And now the big question is, okay, can we essentially interchange between our knowledge about how to work bipedal robots and what we know about human walking to the benefit of both. So for robots, we want to understand how we can walk robustly, fast, and efficient. And for humans, we want to have a better understanding how the biomechanics work for rehabilitation and remobilization. And here, as the conclusion of my presentation, I'd like to come to the research challenges I'm trying to address, which are also related here. The main research challenges I'm currently working on is the mechanics of initiating leg swing in human walking, determining control objectives in leg locomotion, and the applicability of control concepts derived from biomechanics to bipedal robots. And here again, if we see this heel-off and single support, what does that mean? So we have, essentially from a balancing perspective, it seems like a stupid idea. So we reduce the polygon of support, we only have the toes to essentially balance ourselves, and it makes keeping balance harder. But in human walking, we have a competing problem, and I think we have the same problem in walking in robots. We have very little time to bring our leg to the front in order to get to the next step. So if you just look a little bit into gait timing while walking is, of course, the slower gait. We have a cycle time that means, for example, touchdown of the right leg to next touchdown of the same leg of about 0.9 seconds. But the contact time is 61% compared to 41% in running. In running, we have shorter cycle times, but we have flight phases, and we have support phases where only one leg is in contact with the ground, and 2 flight phases plus 1 support phase give me the time for swinging my leg forward. And in running, this is 47 seconds. In walking, it's only 39 seconds that I have to get my leg forward. Okay, so this is a real issue that we have here. We have to get our leg, recirculate our leg much faster in walking than we would have in running. And so the intuitive sequence for getting your leg forward that is often used is we shift the support from the trailing leg to the leading leg. We then lift up the trailing leg, swing it forward, put it down again. And here we are, and we are ready for the next step. So what is active leg protection in short periods of time is adding substantial work to what we have to expand for the bipedal robot. And thus he looked into other ways to bring your leg forward, and what was inspiring the curiosity of biomechanists was always a high power peak at the end of single support. And just as a general statement, to introduce this effect, passive elastic structures can amplify power in catapult mechanisms. What we see here, slow loading of the catapult into an elastic structure. The force stays the same, but because we are unloading against a smaller mass. So you can imagine the loading force as a high mass. This is loading the catapult, and then a small mass, essentially just a lever with a projectile, accelerated by the same force it was loading with, is amplifying the power output. And we see something similar in our leg, and I think a couple of you might have seen this already. So what we see here is essentially an abstraction of the human leg. We have the ankle joint, the knee joint, the hip joint. We have two main muscles that span the ankle joint and generate torque around the ankle joint. The soleus and the gastrocnemius muscle. Gastrocnemius being the bioarticular muscle, so spanning two joints, the soleus just spanning one joint, and while our body is tipping over the ankle joint gets loaded. So there is essentially an extending torque building up. So the torque tries to extend the ankle, but our body mass is preventing it from doing so while we tilt over our ankle. And what we see here in the power graph is negative power. So we essentially have a motion in the opposite direction of the action of the torque in the ankle, and we see this pretty slow loading with not too high power, let's say. So I think about 25 watts is still substantial, but it's not too high. But what happens after loading is completed? And what we see here is this dark gray area as single support. We'll see second light gray area as double support. And then we see this unloading, this high power unloading here. And now, when we think about it, when we look at it, this high power is not produced by muscles. Muscles aren't even able to produce this ankle power that we are seeing. So essentially what we can hypothesize is that we have some unloading going on here, in the sense that we were loading our ankle joint with a large mass, which is the kinetic energy of our entire body, tilting over the ankle joint on a pretty much straight leg, and now we are buckling our knee. And now our ankle joint can unload against the much smaller mass of the leg and bring it forward. If you look at the change in impulse of the leg throughout this phase, from the beginning of unloading, which is here, where the power becomes positive, to the end of stance, when the leg goes into flight. So we see here the impulse of the leg and the impulse of the remaining body. So the remaining body being the upper body and the leg. We see that both impulses change direction, and we see that this seems to become larger. Here it might not be so clear. So essentially, if you look at the relative impulses, so we look at the relative change in velocity over beginning to end, we see that the leg gets accelerated, gains a lot of velocity throughout this phase in forward direction, whereas the rest of the body is essentially decelerated, gains a little bit velocity in the upward direction. And so this is published work, but there are still a couple of open questions. And the questions are, how does the foot facilitate the loading of the ankle joint? So is our foot as a lever indicative of an evolution that facilitated this catapult mechanism? One important part, so in the catapult we saw in the video, we have a locking mechanism which is called an escapement. So we essentially just put, we lock the joint, and unless we unlock it, the mechanism or the whole catapult do not unload. We don't have something similar in our leg. So in our leg, what we call the catch of the catapult, this locking mechanism, is our knee, but obviously we are never locking it entirely, so there's no escaping. So this is essentially just the dynamic balance of forces and torques which allow our ankle to be loaded and then at a certain point unload against the rest of the leg. And this is something we still want to look at. And then one big question is, how do the three involved joints, hip, knee, and ankle, coordinate with each other? This is essentially work I'm planning to do in the upcoming month. Also, I'm planning to apply for a grant for investigating this, and so I'd like to come to the end of my talk at this point. So the take-home message is, I hope I got across, and I'm looking forward to discuss with you, is CMP and COP are similar but distinct mechanical concepts. Anthropomorphic robots have come a long way over the last decades and shown impressive performance in a variety of fields. I'm still convinced that adding bio-inspired functionality adds potential for more performance and better understanding of human biomechanics. And with that, I'd like to thank you for your attention. I hope I met at least parts of your expectations, and I'm looking forward for your questions.
Time for questions.
You have shown some very interesting results from numerical models. Are you also thinking about comparing those numerically obtained results with measurements on your robot over here, or measurements on human beings?
So we actually have compared it already to human experimental data. We have shown that the string mouse model captures the dynamics of running really well. It captures the
Running.
Of running, yes.
Right.
So, and I think part of the reason is that in running, all our three joints essentially operate in sync, so they all flex and extend at the same time. And it seems that we can abstract that as a linear spring, and it shows like the frequency, the timing, the amplitudes of the ground reaction forces. It predicts them in a very good way, I would say.
Right.
For walking, the shape is still the same, but the timing is a little bit off. And I think the reason there is that these mechanisms, like these catapult mechanisms that I just presented, cannot be captured by the simple model. So there, the general dynamics are still similar to what we see. So given that it's a very simple model, it is surprisingly good, I would still argue. But for walking, there are more complex mechanisms involved that the simple model can't capture. I was planning to also look into the data from Lola, but as most from Lola from our Viking robot. But my time just ran out last week, so I wasn't able to do that yet.
The most logical
Yes.
choice to first take Lola.
Yes.
It's less complex than human being.
Yes.
And if you can,
Yes. No.
if you
I'm
can model that already, that would be very nice.
yes. I'm absolutely planning to do that. I think there are some interesting parallels for the ZMP study. As in Lola, the ZMP is planned to stay within the polygon of support at all times with a safety margin. I wasn't expecting too much of a surprise there, so this is where I decided, okay, I just can't put it into the animation.
You can make it full, can you, or
Pardon?
Lola? You can also make it thick. I mean, it will be safe for the
Theoretically.
robot itself because it's hanging on
Yes.
wires, I guess. So
I'm
it
just-
will not really fall down.
I'm discussing this with the PhD students since a while, and they're quite reluctant to go for it. So, Lola is a complex machine, and every time something breaks, it takes a lot of time to fix it. And also my own time as a roboticist, like 80 to 95% of working on a robot is fixing it. And so you are kind of reluctant after a while to do crazy stuff with your robot.
Yeah, but there's a projected flow is not so good.
This looks like for me.
Yeah, it's called Müller.
Mm-hmm.
Well, what he's doing is a bit separate, but
Yeah.
it's part of the discussion.
But I'm coming from the Jena group, so this is probably what is echoing.
So I have a question on the flight time in walking, so I mean the swing phase or?
Yes,
the mo-
yes. So this is the time that you have in order to bring your leg forward.
Okay, that's what you call a flight time.
Yes, so it's always a little bit problematic if you look at one leg or if you look into the entire system. Of course, in walking you don't have a flight phase, so at all times at least one leg is in the ground. But if you look at it from a single leg perspective, you have an alteration of stance time and swing time or flight time, if you like. So this is the time that allows you to swing the leg forward.
Do you know the time of the real flight time, so for both legs, how long it is in human running?
In human running, like yes, I know that it's pretty short, like something like 7 to 8 milliseconds.
Ah, okay.
But I've data on that.
I really loved it because I never really understood the difference between CMP and CUP, so that's really good. So I think that the very essential message is that the CMP is the point where you should have to have your reaction forces so that your angular momentum is unchanged.
Yes.
Just so that you're not changing the rotation theta times omega.
Yes.
And so if in Luna we plan the CMP to be in the polygon of support, it means that we always can prevent Lola to change its angular momentum.
Yes.
That's what we do. But the human doesn't do that, right? The human
This
allows
is
the angular momentum to be changed.
yes. So and like the ZMP in its original definition only looks at the angular momentum of the foot.
Of the foot.
Yes. So it essentially says that your foot will keep plane contact with the ground if this is essentially this. So this is what, one second, this is what Ruka formulated. So he says the dynamics, and this includes like there is a change of angular momentum in the mechanism above,
Okay,
but
so
we don't care about that.
It's taken care of by the moment that you're planning.
Yes, so essentially whatever my mechanism above does will show up as reaction forces in my ankle. And so the only thing I really care about is to not change the angular momentum of my foot, and I can do that by calculating my CMP to be within the area of support. Because then these forces and torques will cancel each other out around the CMP, considering of course this contribution. So this is the general idea. So it doesn't say anything about the angular momentum of your upper body, of your entire system. And oftentimes, like I think I have seen in other publications that they also force the change in angular momentum of the entire system to be 0. You can put that in, but this is not the, I would say, original definition.
But it would be the same if the moment N is coming from the chain of angular momentum
Yes.
from the top, so it's
Yeah.
the limit system. Okay. So it means that if the CMP is in front of the polygon of support, it means that you are obligatory increasing your angular momentum forward.
Yes.
You're pushing the
Yes. So you're tipping forward, and though, if you think about it, so the question really is what is going on with the torque here. So here again, like if you accelerate forward, your reaction force will be backward. You will push your zero moment point backward, so you will avoid essentially your foot from tipping forward if you do that. And the same if you essentially generate, like I think you would have, and always get this messed up. So I think you have to also bend forward, so add an angular momentum forward in order to avoid tipping forward. So you would have to change your angular momentum of your entire system to move forward in order to bring the ZMP backwards. So it doesn't really mandate any change of angular momentum of the upper body, I would say.
Okay, so thank you, Daniel.